Hi, in this segment, I'm going to explain how to find the square root of a number in a modular arithmetic context, especially if the group is a composite group like Zn. Okay, n stands for integer. Z is the set of all numbers, integer numbers. In this context, it means 0, 1, 2, all the way until n minus 1. So in cryptography, usually we define a multiplicative group. So as follows, we will do Zn star, okay, which means all numbers, let me call it x, such that GCD of x comma n is 1. We talked about Zn star in earlier videos. So this is basically the Zn star group. Okay. What is n? N is usually made of two large primes, equal size primes. Given n, it's difficult to find p into q. Given p into q, it's easy to find n. We just have to multiply. So this usually, from a computational complexity theory point of view, this is considered as believed to be an NP problem, meaning it's easy to verify the answer. It's difficult to factor the given number n. Okay, that's a little note aside. Let's get back to the goal of the video is to talk about this particular group. Okay, I wanted to write an algorithm for this particular problem. The problem is this: suppose I give you a number y, right? And the goal is to find a number x such that if you do x square, right? X square mod n is y. So here, this is the problem I would like to solve. Given y, right? Find an x such that x square congruent to y mod n. Okay. You can't, as far as I know, you can't solve this today. You would need the prime factors of n as well. So given y, p, and q, we can find an x such that x square is congruent to y mod n. This problem can be solved. Okay, and I'm going to show to you a technique that you can easily use to find such an x. Okay, so the technique I'm going to use is based on Euler's theorem. So we learned in the previous segment that a number x or a number y, let's use y. Y is a quadratic residue if and only if x power p minus 1 by 2 is congruent to 1 mod p, then we say x must be a quadratic residue, meaning you could write x as power of 2. Okay, so to be consistent with the notation, let me clear this thing to avoid any confusion. I would say y is a quadratic residue if this condition satisfies. Okay, so here y is a quadratic residue because y is congruent to x square. Okay, just to be clear, we call y a quadratic residue. Okay, because we find an x such that x square is congruent to y mod n. Okay, this theorem, Euler's criterion, itself immediately doesn't give you an x, but we can do a little tweak and then we can get an x as follows. We are going to make one more assumption about the structure of p and q. If we make an assumption that p is congruent to 3 mod 4 and the q is also congruent to 3 mod 4, we can, this is called Bloom integer, by the way, we can easily find the square root. Okay, I must say there are 4 square roots in the context of z star n being product of 2 primes p and q. We talked about this in other segments, so please watch that. All right, so in this case, we do know that if we have this assumption p and q being congruent to 3 mod 4, it's easy to find the square root of y. Square root of y is nothing but y power p plus 1 by 4 is the square root of y, because if you square this thing, let me show you how we can verify it easily. Just take y power p plus 1 by 4 and square it. Okay, you square it, you get y power p plus 1 by 2, which is nothing but y power p minus 1 by 2 into y. Okay, just basic power of arithmetics, power of exponent rule. This is 1 because we know this from this equation. Therefore, we get y here. As you can see, it's easy to find the square root of y if this condition is true. Okay, it's not super hard even if this condition is violated. There's a randomized algorithm. But for now, let's assume we have the p and q, this structure, the Bloom integer structure. Okay, so now let's get back to the bigger problem I want to solve is not in mod p or q. I want to solve it in mod n, right? I want to be able to find the square root of y in mod n, right? Question is to find the square root of y in mod n. Okay, how do I do that? I'm going to make use of my Chinese remainder theorem discussion, which we had in other videos. All I'm going to do is as follows. So now I'm going to erase this part. Okay, all I'm going to do is make use of the Euler's criterion, right, and do a small exponent trick to solve this problem very easily. Okay, so all I'm going to do is as follows. Let's assume y belongs to quadratic residue, right? We know y belongs to quadratic residue, but our goal is to find square root of y. Okay, so how do I do that? All I'm going to do is go back to this equation number 1. So I do know that I can raise the equation number 1 to the power of q minus 1 by 2, because that's allowed in model arithmetic. You can raise the power on both sides. So it's just going to be still 1 mod p. Okay, and now we are going to do a small trick. We multiply both sides by y. So what will happen now is we get p minus 1 into q minus 1, right, by 4 plus 1, right? Because I'm multiplying both sides by y, we can add the exponent. Okay, is y mod p. Okay, so what is the next thing I need to do is, okay, here's mod p. Okay, symmetrically you will be able to obtain another equation. Let's call this as 2 by just replacing by exchanging p and q basically. So which means we will be able to say that y power p minus 1, let me first simplify this one moment, into q minus 1 plus 4 by 4. Okay. Okay, this is congruent to y mod p. Okay, very good. So we can now, let me call this as equation 2 because this is equivalent. Okay, we can forget about this. So what about equation 3? I was telling, just start with y power q minus 1 by 2 and raise it to p power raise it to p minus 1 by 2. So that means we'll have the same left hand side, but the right hand side will be slightly different. Okay, it still be y, but it will be mod q. Okay, so now we can apply Chinese remainder theorem because we have p and q are relatively prime. We have some number, right? This number. We did mod p, we got y, and we had the same number. We did mod q, we got y. Okay, that means the number must have been this number because this is the number that we started with. We do mod p, we get y. We do mod q, we get y. So what we found out is that y power p minus 1 q minus 1 plus 4 by 4 is congruent to y mod p as well as y mod q. Therefore, it's congruent to the same in mod n. Okay, because of the Chinese remainder theorem. Okay, now we can easily solve this problem as follows. Okay, so I'm going to make a claim now that the square root of y is nothing but y power p minus 1 I must say one square root. There are three more, but we are only interested in a square root which is also quadratic residue. Okay, at this point, plus 4 by 8. Okay, this will be my square root of y in mod n. Okay, let me rephrase this. Given a number y in mod n, we can find the root y. Okay, that's what we did. This is basically the answer for root y. If you multiply this 2 times, this portion, and do a mod n, you will get y. That's the idea of root anyways, right? Square root of 16 is 4 because 4 times 4 is 16. All right, so to summarize the long story short, we use the Chinese remainder theorem to find the square root in mod p and in mod q, and then we put together the square root in mod n. Okay. So whenever you have a Chinese remainder theorem context like this, the left-hand side is the same for both mod p and mod q, and the congruence is also same. Then you could say the left-hand side is the number in mod n. Okay, because that's basically the definition of how Chinese remainder theorem works. All right, so now I will show you some simple demo of how I can find the square root, one of the square roots of a number in mod n. Okay. All right, let's do that. So what you're seeing is a simple proof of concept program. I'm going to generate small primes for the sake of demo. You could try it 20, 40, it will still work. I tried it, but it's going to be a little slow. So I'm going to generate first a composite prime number made of 512-bit. Okay, basically both p and q will be only 256-bit. Okay, so you get n, p, and q. They must be different primes. That's the reason I do this. And then I randomly generate a number y, and I wanted to show to you how to find the square root of y. Okay, and the number y that I'm randomly generating is already a part of quadratic residue. I know for sure square root exists. That's the reason I'm doing it in this way, that I generate a number r, and I use Euler's criterion to make sure the number r that I get back is a quadratic residue in mod n, right? This is something that we talked about in other segments, so I'll not keep explaining that. And then I'm going to assert that the is quadratic residue function returns true, because I know for sure my quadratic residue must satisfy, but I just want to get more confidence. And then I'm going to do a square root of this number y as per the algorithm. Now let's look into the square root algorithm. Okay, it's exactly the same as what I drew on the whiteboard. Square root of y is nothing but y power p minus 1 times q minus 1 plus 4 by 8 in mod n. That's it. This is the only one-liner code. And we can assert that when we multiply the square root 2 times, we get the original number, right? Square root of 16 is 4 because 4 into 4 is 16. Okay, that's basically what we are doing here also. And then we assert also that the square root itself is a quadratic residue, which is true because of the Bloom integer structure that I talked about. Okay, so that's basically it. So we have a way now to find square root of a number in a composite group context, provided that we are given the prime factors of the composite number. Okay, I need this for a couple of other videos. That's the reason I am first introducing you to the notion of how to find a square root of a quadratic residue. And the square root itself is a quadratic residue. You probably noticed that I added another assert statement that it is a quadratic residue as well. And there is only one such square root, okay, for Bloom integer. That's a novel property. All right, thank you very much for your attention.